Now we turn to conditional expectation as we continue to review the ideas of probability as we lay mathematical foundations for stochastic processes. Conditional expectation. Um, Conditional expectation describes the expected value of a random variable given some information. So if x and y are random variables, the conditional expectation, that is the expectation of x given y, represent the average value of x when y is known. So conditional expectation is fundamental in probability theory, statistics, stochastic processes, which this playlist is about, machine learning, and economics. The intuition is that the ordinary expectation of x, is the average value of x over all possible outcomes. Okay, so conditional expectation, which is the expectation of x given y, is the average value of x when the value of y is known. The example interpretation will be if x is exam score and y is hours of study, then we can say that the expected value of x given y is 5, means that the average exam score among students who studied 5 hours, So this is like that. So what is the exam score of a student, the expected value, the average score of a student, given that the students studied for 5 hours, like that. Okay. So definition for the discrete case now. So let x and y be discrete random variables. The conditional expectation of x given y is equal to y is expected value of x given y equals y is summation over x of x multiplied by p of x equals x and y equals y. Well, we already have an idea of this because we talked about expected expectation in an earlier video where we saw that for discrete cases, expectation is the summation of x multiplied by its probability summed up like that. So, but in this case, we look at it in this conditional sense. So steps to compute, find the value y equals y first, then determine the conditional distribution probability of x equals x given y equals y, and compute the weighted average of x. So the weighted average is basically the value multiplied by its probability, and you do all that and sum everything up. So look at the discrete example we have right here. Suppose the joint distribution of x and y is what we have in the table. Uh, okay, let me see if I can fit everything together at once. Okay, I think it works. So suppose the joint distribution of x and y is this. So x 1, 2, 3, 4, y 0, 0, 0, 0, 0, 1, 1, and the probability 0 0.2, 0 0.3, 0 0.1, 0 0.4. So you want to compute the expectation that x given that y is equal to 0. So first, you want to compute that what's the probability that y is equal to 0, right? Probability that y is 0, is 0. So y can be 0 with probability 0.1, y can be 0 with probability 0.3. So the total probability that y is 0 is 0.5. Then with that in place now, you want to compute probability that x is equal to 1 given y is equal to 0, right? So you now want to compute all these things given that y is 0. So probability that x is 1 given that y is 0, that is the probability that x is 1 is actually 0.2 divided by probability that y is 0, which we already have to be 0.5. That's 0.2 divided by 0.5, that's 0.4. And probability that x is equal to 2 given that y is 0, that is 0.3. That's the probability that x is 2, 0.3 all over probability that y is 0. So that's 0.6. Therefore, you can now say expected value of x given y equals 0 is now the weighted average, right? So you have 1 multiplied by 0.4, x is 1. So 0.4 plus when x is 2 multiplied by the probability 0.6. So you have everything together. 1 times 0.4 is 0.4, 2 times 0.6 is 1.2. So 0.4 plus 1.2 is 1.6. And that gives the expected value of x given that y is equal to 0. So we then have definition for the continuous case. If x and y are continuous random variables, then the expected value of x given y is equal to integral of x multiplied by fx given y of x given y dx, where f sub x given y of x given y equals f sub xy into xy all over f sub y of y. Here, f of x sub xy into xy is the joint density, where and f of y sub y is the marginal density of y, like that. So everything still derives from the basic general idea of expectation. So conditional expectation as a random variable. Now, the conditional expectation ex given y is itself a random variable. So the conditional expectation as a random variable now. That conditional expectation is also a random variable. This is because its value its value depends on y, right? So example, if the expected value of x given y equals y is 2y, then we say that the expected value of x given y is equal to 2y altogether. So thus the conditional expectation becomes a function of y. So with that, by that token, we say that the conditional expectation is a random variable. So talking about properties of conditional expectation now, we've seen the idea of linearity for under expectation. So the expected value of ax plus bz given y would simply be there's a multiplied by the expected value of x given y plus b multiplied by the value of z given y easily. And then talking about independence, if x is independent of y, then we say that the expected value of x given y is simply expected value of x because y doesn't affect it in any way. So that's knowing y gives no additional information about x. Then function of y now. So if x is equal to g of y, then we say that the expected value of x given y is actually a function of y, g of y, because once y is known, x is automatically determined. Then that takes us to the idea of law that takes us to the law of total expectation. So the law of total expectations states that the expected value of x is equal to the expected value of x given y, right? This means the overall expectation can be computed in two stages. So the overall expectation can be computed in two stages. First of all, compute the expected value of x given y, and then you now calculate the expected value of that expected value you've calculated. This means the overall expectation can be computed in two stages. And so first, compute the conditional expectation of x for each value of y, and take the expectation of those values over the distribution of y. So to prove the discrete case, now we see that if we start from the definition, expected value of x, that is summation over x of x multiplied by p of x equals x. Using conditional probability, now we know that probability that x is equal to x is equal to summation over y of p of x equals x, given y equals multiplied by p of y equals y, like that. So we substitute to the expectation right here, and then we rearrange the sums like this, and then we recognize that this expression is actually the expected value of x given y equals y. Therefore, the expected value of x is this expression, which is actually actually tells us that the expected value of x is the expected value of the expected value of x given y, like that. So we have law of total expectation example. So imagine that y is weather and x is daily ice cream sales. So now once you look at the expected value of the expected value of ice cream sales given the kind of weather you have. So imagine that the weather is sunny with probability 0.6 and the expected value of x given y is 100. Then the weather is rainy with probability 0.4 and the expected value of x given y is 40. So you compute expected value of x to be the expected value of x given y, right? That is 0.6 times 100 plus 0.4 times 40, because that's simply the expected value of the expected value of x given y. So you have 60 plus 16 and the expected value becomes 76. So it means that based on this analysis, the expected value of x here, the expected ice cream sales, given this particular situation, will be 76, like that. So we move on to the tower property. The tower property generalizes the law of total expectation. Um, the total property, the property generalizes the law of total expectation. If we have nested conditioning variables y and z, then the expected value of x given y and y and z given y, it's that nested thing is equal to expected value of x given y all overall. So the interpretation is that the first condition on y and z, so we first have a condition on y and z, then average over z, the result is the same as conditioning only y. That's the tower property. So it's like you have some nesting going on and you try to resolve them one after the other until you get to the last. So general form now, let G and H be sigma algebras. Or sigma algebras, we already know that they are like event space. So let G and H be sigma algebras with G being a subset of H. Then we say that the expected value of the expected value of H, X given H, given G is equal to the expected value of X given G. Okay? So this expresses the idea that conditioning twice collapses to the smaller information set like that. So example of the tower property now, we want to demonstrate that in this place. So suppose that X is final exam score and Z is homework score, Y is attendance. First, compute the expected value of X given Y and Z, which uses full information. Then you compute the expected value of what you computed up here already, given Y already. So this averages out our Z and the result equals expected value of X given Y, like that. So we have the conditional expectation as best predictor. So a key result probability theory states that the expected value of X given Y is the function of Y that minimizes the expected value of X minus G of Y, all raised to power 2 over all functions G, comma G of Y. Thus, conditional expectation is the best mean square predictor of X given Y. So these ideas form the base for this idea forms the basis of regression, statistical learning, and signal processing. In summary, we see that in summary, let me see if I can put everything together in one slide, in one show, so to speak. So in summary, we see that conditional expectation, which is given as expected value of X given Y, represent the expected value of X when Y is known. So key result, the expected value of X given Y equals Y is equal to summation over X of X multiplied by probability that X is X, given that Y is equal to Y, or for the continuous case. This is for the discrete case, this is for the continuous case. Then we have the law of total expectation, which tells us that the expected value of X is the same thing as the expected value of the expected value of X given Y. So that means that you have that nested expectations. So expectation of X given Y, if you take the expectation of X given Y, it is as good as taking the expectation of X itself. So then you have the tower property, which even involves another layer of variables like that. And then we have our practice problems, which can be easily handled by just following the examples up there, especially knowing that this is a review of the ideas of probability. To solve the following problems involving conditional expectation, the law of total expectation, and the tower property. So let X and Y be discrete random variables with joint probabilities. So compute the expected value of X given Y is 0. So it's exactly like what we did before. Use the same distribution as problem 1. Compute the expected value of X given that Y is 1. So now you shift your gaze to these two values now. All right. And then you keep moving. So here we have the total law of total expectation. Then problem 4 now, you have probability of Y equals 0 equals 0.7. Probability of Y equals 1 is 0.3. Given that the expectation of uh the expectation of X given Y equals 0 is 5, and the expectation of X given that Y equals 1 is 10. So compute expectation of X. Easy. Just multiply each expectation by the probability, the corresponding probability. So 0.7 times 5, that's 3.5. 0.3 times 10, that's 3. So 3.5 plus 3, that's 6.5. That's your value of expectation of X easily. So for question 5 and 6 now, you suppose that expected value of X given Y is 3Y plus 2 and expected value of Y is 4. So then you compute expected value of X like that. Okay, so you want to try that out. Then problem 6, you have this whole thing going on again. So yeah, so for 7, all that. So I'll just flash them as we go step by step. So if you try any and you still feel you need help, you can just let me know. I may just make another video just to explain whichever one you think is problematic for you if you need to do it. Okay. So 14 to 16 here now, and then 17 to 17 to 19, and then we have 20. So maybe I can show 18, 19, and 20 together like this. So, yeah, so with this, we come to the end of this interesting video about conditional expectation as as it is associated with review of concept of probability as we lay foundations for stochastic processes. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed already, I thank you very much for doing that. If you haven't subscribed, this is the good time to subscribe and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of the channel by clicking on join. That gives you special privileges like getting to see some videos first before other people, or seeing some videos exclusively because you're a member of the channel. You can ask for PDF copies of my lecture notes, and we can also hang out to discuss whatever interests you on this channel. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing math right. Bye.